An annuity is any sequence of equally spaced periodic payments. The type we will study here is an ordinary annuity, in which the payments are made at the end of each of the time intervals. The future value of an annuity is the sum of all the payments plus the interest that was earned. Let's start with an example. Let's suppose that we deposit $100 into an account every 6 months for 3 years. The account pays 6% interest and it's compounded semi-annually. How much money will be in the account at the end of 3 years? So we're going to start out with the first compounding period, which will last for 6 months. Okay, so our amount will be $100 because nothing happens until the very end of the first compounding period. The payments occur at the end of the period. So we are going to consider that the account is sitting on empty for one compounding period. Now, at the second compounding period, okay, at the beginning of the compounding period, we have the $100, but it will get multiplied by, let's go off to the side, my periodic interest rate, is equal to R over M. So 0.06 divided by 2, which is 0.03. And my A, remember, is equal to P times 1 plus R over M. So it'll be whatever my principal is times 1.03. Okay, that's what we're going to use here. So here, the $100 that we deposited at the end of the previous time will now be sitting for the entire second period, and therefore it will earn interest. How much will that 100 grow to? Will be 100 times that 1.03. In other words, that 100 is serving as the principal. Then, the very end, we are going to add on another $100. This is the new payment. Okay, and remember this $100 was the first payment, which occurred at the end of the first compounding period. Now we move to the third compounding period. Now our new principal is, for this first term, is the 100 times 1.03. That's the principal, so that would be the P over here, but then it's getting multiplied by 1.03 again. So now we have 100 times 1.03 squared. That payment at the end of the preceding compounding period, now we have $100, but now that gets to sit there for the whole entire third period. So it gets multiplied by 1.03. And then what do we do at the very end? We tack on our new third payment. Now we move to the fourth compounding period. Each of our amounts will get multiplied by 1.03. So that gives me 100. And now I'm going to have my 1.03 cubed because it got multiplied by 1.03 again. The second term, I will now have 1.03 squared. And the third term, well, I'll have my 1.03. And then I will tack on my next payment. Let's do just one more. I think you're starting to see the pattern. Okay, so each of these gets multiplied by 1.03, so the power goes up each time. And then we tack on our payment, which has not yet had a chance to earn interest. And so then we could keep doing this. And of course, We don't want to have to do this for many compounding periods, but it's worthwhile to see the process. You can see how something like this will follow a consistent pattern, and that there ought to be a way to generalize this into a formula. Notice we could factor 100 out of each of these terms. And so the 100 could be factored out to the side. That'll be our payment. And then there just needs to be a way to combine all those exponents. I won't get into the algebraic details here of how that will be done. I will just show you the formula that results. Future value is equal to payment times 1 plus I raised to the n minus 1 all over I. Okay, our I here is R over M. You could write that into the formula. I've left it as I just to cut down on the clutter, but that's what it is. N is once again the number of compounding periods, and so that tells me that I can get that by multiplying the number per year times the number of years. And our future value is the amount after interest is accumulated. This formula is based on the fact that the periodic payments are at the end of the compounding period. If you make them at the beginning, there is an adjustment to the formula. It will not look exactly like this, although of course it will be similar. Also notice that the periodic payments and the number of payments per year and the number of quarterly, scratch that, we have to have payments at the end of each compounding period. That means that the number of compounding periods has to match the number of payments, and also the payments must be at the end of the compounding period. So that means we cannot have monthly payments and quarterly compounding periods. They have to match. They either have to both be monthly or both be quarterly or both be whatever matching number. Let's move on to an example. What is the value of an annuity? That means future value. Remember, it says end of 10 years, so that's future value. If $1,000 is deposited every 3 months into an account that earns 8% interest and is compounded quarterly. And then we want to determine how much of this is interest. So first of all, let's write down our formula. Future value is equal to payment times 1 plus I to the n minus 1, all divided by I. And now we're going to write down what each of our variables is. So for R, we have 0.08. Number of compounding periods per year is 4. And so that means my I, which remember is R over M, that'll be 0.08 over 4. This one you could simplify it here. Many of them, if you do that and get a decimal, you'll get something that does not terminate, so you'll have rounding error. So I'm going to just leave mine in its unsimplified version like this. Okay, sorry, I still can't read that. 0.08 over 4, that's better. Okay, our payment is equal to $1,000. And that's all we need. Actually, we need N, which is MT, the total number of payments, which will be the same as the total number of compounding periods since they match. Notice we are compounded quarterly. We are depositing money every 3 months. Every 3 months is 1 quarter, so those match. So we have 4 per year times 10 years, which is 40. So I have $1,000 times 1 plus 0.08 over 4 raised to the 40th minus 1, all divided by 0.08 over 4. Calculate this on your calculator. Make sure you do it along with me so that you get comfortable making this calculation. It's usually best to start with the most complicated part first, so I would suggest starting with the part in parentheses in the numerator, raise it to the 40th, subtract 1 from that answer, and get an answer for your numerator. Then divide it by 0.08 over 4, and then multiply the whole thing by 1,000. You should get 60,000 401 and 98 cents. Now we want to figure out how much interest was paid. To do this, we have to remember that interest is the cost of borrowing money. Okay? Everything that is not principal that was paid directly into the account, everything extra is interest. So what we want to do is figure out the total of our payments. What will that be? Well, there are 40 of them. We multiply by the size of each payment, which is $1,000. Sorry, $1,000. So we end up with $40,000. Okay, and so then my interest is equal to my future value minus the total of the payments. In other words, everything extra that did not come from a payment is interest. So I take my 60,000, 401.98, and I subtract the $40,000 in payments, and I end up with total interest of $20,401.98. Let's move on. Let's suppose that the parents of a newborn baby set up an account to cover the cost of college. On the child's birthday each year, starting on the first birthday and ending on the 18th, they deposit money into the account, and that account pays 7% compounded annually. Again, we note that the compounding periods match the payments once a year. How much should they deposit annually in order to have $100,000 available for college when the child turns 18? This is what we call a sinking fund. We keep sinking money into the fund so that in the future we will have a large lump sum for a specific purpose, in this case, college. So we know we need the future value because the lump sum we are looking for is occurring in the future as opposed to present value when the lump sum would be occurring at the beginning before the interest. Here our lump sum is occurring after the interest, so we want future value 1 plus I to the n minus 1 all over I. So my rate is 0.07. My number of compounding periods per year is 1 because it is compounded annually. Therefore my I, which is R over M, is 0.07 over 1, which is 0.07. My future value that I want to have is $100,000. And we want to determine the payment. So I put everything into the formula. My $100,000 goes on the left side. My N, let's determine our N. Didn't do that part. My N is equal to MT It was compounded once per year times 18 years, so there will be 18 payments, 18 compounded periods. Okay, so we solve this for payment. I would suggest calculating the part in the brackets first. Start with the numerator, then divide by the denominator, get an answer, and that gives you the part in the brackets. Then take 100,000, divide by that answer that you had found previously. Depends on what calculator you have, the best way to do it. But make sure you do it along with me. You should end up with a payment of $2,941.26, which of course is a decimal approximation, but that's the amount we're going to write checks for, so we are going to round to the nearest cent. And of course, as always, ask yourself if that answer seems reasonable. Okay, let's suppose that at the age of 25, Joe decides to start saving for retirement. He will deposit $300 each month into an account that earns 6% interest compounded monthly. He does this until he turns 40. Then he quits making payments, lets the money sit, but it still earns that same interest rate until he turns 65. We want to know how much he will have when he turns 65. Okay, well, before we figure out how much he has when he turns 65, we need to figure out what he has when he turns 40. In other words, from 25 to 40 he is making payments, and then he stops. So what we need to do is figure out what he has at age 40. Which formula will we use? Well, ask yourself, are there periodic payments? Yes, then we need an annuity formula. Because our lump sum is occurring at the end, after the interest, we need the future value annuity formula. So that is future value equals payment times 1 plus I to the n minus 1 all over I. Okay, and so my I is R over M, so that is 0.06 divided by the number of compounding periods, which is 12. My N is the number of compounding periods, which is also the number of payments, MT. So 12 times how many years? 15, which gives me 180. Why 15? Because that's age 40 minus age 25. In other words, he is doing this for 15 years. That's how many payments he is making. And his payment is $300. So we put all that into our formula. And you should end up with $87,245.61. Okay. Now this amount will just sit while earning interest until he is 65. Okay, so we need to figure out how much it will grow. So at age 65, how much will he have? Okay, well, what has that money been doing? That money's just sitting there, so we cannot use the annuity formula. The annuity formula involves periodic payments. We do not have any periodic payments. We just have interest being compounded. So that means we're going to use our compound interest formula. A equals P times 1 plus R over M to the N. And we'll write down everything for that. My principal is what? How much money is earning interest? The 87 to 45.61. That's how much money is earning interest. My R over M is still 0.06 over 12. This time my N is equal to the number per year, number of compounding periods per year times the number of years, so that will be 12 times how many years? 20. Why 20? Because if we do, sorry, it should be 25, my mistake. Because if we do 65 minus 40, that gives me 25 years. So we do 12 times 25. That gives me 300 compounding periods. So now my amount that he has is 87 to 45.61 times 1 plus 0.06 over 12, all raised to the 300th power. Work all this out, and you should end up with 389,549 and 1 cent. Now we move to the second part of the question. We have another gentleman, Tom, who gets a late start and doesn't start saving until he turns 40. How much will he have to deposit each month, assuming the same interest rate, in order to have the same amount as Joe when he turns 65? Okay, so is he making monthly payments? Yes, he is. That means we're going to need the future value of an annuity formula. It involves payments. Okay, so we have future value is equal to payments times 1 plus I to the n minus 1 all over I. Okay, we're writing down our formula so that we can see everything we need. Now we're going to go off to the side, make sure we know what to put in there. We do not know our payment, so I'll mark that with a question mark. Do we know our future value? Well, yes, we do. We want him to have the same amount as Joe. How much did Joe have? Joe had 389,549.01. So that's how much Tom wants to have. Our M is still 12, which means our I is still R over M, which in our case is 0.06 over 12. Our N is equal to MT, which is equal to 12 times how many years? 25, because he's saving from age 40 until age 65. So 65 minus 40 is 25. So he's going to do this for 25 years, which means 300 payments. In other words, he's making a payment all that time. Joe's money is just sitting there and earning interest. So Joe has compounding periods. We have payments. Same number, 300. Let's put everything in. So 389,549.01 is equal to our payment times 1 plus R over M to the 300th power minus 1 all over R over M. Work this all out. Again, I suggest starting with the most complicated part first, and then you can go 389,000 divided by whatever answer you get. You should end up with 562.12. This is Tom's monthly payment. Let's just do a very quick comparison. Joe made 180 payments of $300. So he made $54,000 in payments. Tom made 300 payments at $562.12 each. For a total of $168,636 in payments. So at least he got started saving for retirement, but my advice based on this, and I hope you'll agree, is to start early. I hope this helped you to learn a little bit about compound interest and payments and future value. Good luck, and I will see you next time.